Yeah, so I came from math department. So actually, I came to UWM 2002. So this is the first project I did at UWM. Okay, so that's almost more than 50 years ago. So you see, this is all around. Just give you some background on this topic.
Can we start from introduction maybe? Because some of you didn't come last time, right? So maybe a very brief introduction to each one of the right. So that, yeah, Professor Xu is from Math Department. He's a professor, right? Can we start maybe, Brian?
Sure, Brian Armstrong, electrical engineering.
I am Russell Latterman. I'm one of the PhD students in the math department with a statistics emphasis.
I'm Rohit Kate from computer science.
Guang Su from computer science.
Phoenix Doe from the Zerbo School of Public Health.
Chao Zhu from math department in probability.
Spencer Wang from Zilber School of Public Health.
Hi, Yongju Cho from the Zilber School of Public Health.
Zheng Xu from geography department.
Song Honghan from Zilber.
And then from computer science.
And then you from computer science. That's good. Oh, yeah. Professor Zhang from E.
So let's just give you a little bit of background. So actually, I am now still working on the protein simulation. I think that's the long-term project I did. So this is related to the drug designing. I think so. This is how drug designing is related to protein study, because you have to first identify the target protein, and then you want to find the drug which is the chemical compounds interact with the target protein. So this is called the binding problem. So you have the chemical, you have the protein, and then you have to look for the binding sites, and if you identify the drug. So I'm now working on how you're going to do the binding division. So that's a kind of project I did. So we developed models, algorithms, simulate the protein, predict the structure, binding sites. But in this talk, I will going to see how you're going to search for potential drug from the large data sets. That's the major project. I really like this group. So let me really thinking how to continue this project after so many years. So I wish you may get some idea what I do, and then you ask me any question, you may have this informal discussion. Okay, just ask me, then if you have any suggestion or some motivation from my talk, yeah, we can continue to discuss. That's the purpose of this lunch, informal discussion session. Okay. So first, let me just tell you a little bit about the drug designing problem. Okay. So in drug designing, this is one step. So we usually have to find potential drug as needs. So a lead is a chemical compound that can interact with the protein. So what's called the drug? The drug will be some lead that people can take, not harmful to human. So the lead can play like the roles, like we see here, inhibitor role, enhancer role to the protein, so they can cure the disease. But they may not to be a drug because they may hurt people if you take them. So that's a drug and the lead. So that's why we have a large data set of the drug. When you find some compounds, of course we cannot take them. And then one important step is go over, screen the whole data sets to find the one that's similar, that's lab, and then to see any available drugs that are similar to that one. So that's one step in pharmaceutical company to search for a drug. So how to do that? Okay. So of course, how you going to search for a drug? Usually, we have the chemical database. This is I think one large data set. You can search here, find this one. I just today I just checked that one. So now they have you see 180,000 potential drugs.
Is that number the latest number or the number 10 years ago?
This is I just checked today.
Okay.
Yeah, I think about 10 years ago it's about 100,000, 31. Now it's over 180. So this is the speed about 10,000 per year. So they keep growing. I think that they collect this drugs from the literature publication anywhere. I don't know how to do that. Okay, so I think you can find none to get this data sets that's available. So that's the one we use a study. So this is experimental techniques you should for just automatically just do essays projects. So that's called a high throughput screening. Okay. Of course, for us, we're going to computational approach. We set up a virtual database. So that's a real database you do experiments. So computationally, we have to digitize each drug numbers. So we call that virtual data sets. Okay. So for the virtual data sets, usually we have to set up so-called chemical descriptors to characterize each compound numbers. So you think this is a data set. Each row stand for one chemical compound. So per like a column produce a value by a so-called chemical descriptor, describe one property of a compound. So that's the virtual
What's the size
database.
of each descriptor on each row?
On each row, so that's give the number of descriptors to characterize a compound.
How large is it?
That's can be 1,000. Yeah. So depend. So this is a time consuming part. Of course, there is a program package let you do the calculation of these values. When you identify a compound, they're going to produce the values according to program package. According to okay.
Question, how do you characterize each compound by some number?
Okay, I'll give a little bit details, so just later, okay. Now we will, for us, we say, now you have a data set just like that, okay. Each row, okay, represent one chemical compound, okay. So that's called a virtual data set, database. So this is a little bit of idea, so how to define chemical descriptors, to characterize compound. Okay. So this is a research by its own. I don't do that. Okay. So there are many chemists, like a company, just work out such a virtual database. Because this is important step. If we want to use computers to help us develop drugs, this is important step. So digitalize, just like the video, I have to digitalize picture, image, is same thing, like sound, right? Digitalize.
So this has been a standard used by many different companies, right?
Yeah, they have many companies who work out
The same standard.
Yeah. So you see, this is typical like chemical disruptors. For example, number of items. That's obviously you want to know that, right? Of course, here you see the structure. Okay. So this is the part I'm now working out the three-dimensional molecular structure, and then we want to calculate like, the surface area and some volume. Okay. Especially you have some partial atomic charges, and I think most important you have to calculate electrostatics. So that's a lot of properties that you need to know. So how you're going to calculate them, that's an important research area. Of course, we are not to work out that one. So this is a software package. I think that's one popular one to do such a calculation to generate a virtual database. Okay. So this is one. All right, so you can see, I just screening like 7,500 compounds from this database. So this is provided from our collaborator from the Merck company. So that's the data set the use for the drug developments. So first step after I got them, I want to see how this database look like. I just took the non-zero values, distribution. You see, this is the number for compounds. This is the number for descriptors. So from here will be more than 1,000 descriptors. But I think like first like hundreds, several hundreds, mostly just in the front part of this data sets. So that's why I'm going to just cut off here. Just use I usually use 300 descriptors to work out. So based on this observation, okay. So I mean that's actually characterize compounds enough. Use first few hundred descriptors. Because here they still work out. It's a lot of empty. Right? So it means they don't know what the value is for that descriptors. Okay. So that's the one we like. Okay. So let me say what's the fundamental research problems for chemical database analysis. I think this is common for any database. We have to work out such problems. So first one we call the similarity search problems or similarity sampling problems. The second is diversity searching or diversity sampling. Of course, there have some difference. So sampling will be go to statistical approaches. You have to pick a set of samples, right? Okay. We call the searching, that's a deterministic approach, mathematical. Just want to identify a particular one. Okay. So they have some difference. Okay. So this is two basic problems we work, especially for computational scientists, who want to develop fast algorithms to solve them. Now let's just give a little bit like the mathematical framework. Okay, we set up to deal with such problems. Okay, like I say, now we use a vector, just a number vector describe a compound. Okay, and then the database simply a collection of these vectors. Now we can list a database in a matrix. Like I say, this is just a matrix. So now you have a n by m matrix. So n is the number of compound. M is the number of descriptors. Each row represents a chemical or drug. So that's the database we start. Okay. So after we have this database, and then we have to introduce we call the diversity measure. So this is depend on so-called vector norm. I think in literature they have many different definition of norms, particularly designed for database. In my research, I simply use Euclidean distances. Okay. The reason why I do that, I'm going to say that. Okay. So just from the mathematical point of view, I do that. Like chemists, they may use some other norm with some weights. Because based on the experience, to know which describe is more important to get more weights. So you are saying, I think that's a research area. Okay. So that's important. So and then we have to do a so-called scaling. So because you see, this is you have to a sampling. You thought this is a random matrix in some sense. So for example, in my point of view, I can regard each descriptor as a random variable, and then they're going to produce a random value for each kind of compounds. So that's the reason why I'm going to do principal component analysis with the PCA. We call it PCA. Principal component analysis is a statistical tool. So in that point of view, you thought that this is random generated matrix. Then you have to do so-called the mean or expected values, relation. So that's the important for people who study statistics to involve to do further study. So anyhow, this usually people did. Okay. So mathematically, you can simply write a similarity search problem. You see, this is just a typical minimization problem for just the distance between two compounds. So the distance between two compounds indicated similarity. So the distance larger, and of course they are more diverse. If the small, they are similar. So that's the one we use to indicate the similarity using this measure. So we are going to find the smallest distance if for a given there's a given target, you want to find the one most matched one. So that's the similarity search. Now, if for sampling, you're going to find a set. Okay. So not just find one, you're going to find several one. So that's a sampling problems. Okay. Because this is involves some like a random issues, so you have to test several ones. So that's sampling problems. I think most difficult one is called the diversity search problems. So in these problems, you are going to find the so-called representative set. So you have a large data sets. When each time you screening on the data sets to match a potential drug, and you will not check one by one because that's too time consuming. The ideal case is you are going to find a small set. Each member of this small set represents a cluster. So it means all other compounds will have very similar property with this representative. So that's you are going to screening the whole data set. You're going to screening this small set of representatives. But how are you going to construct this representative set? That's actually is a combinatorial optimization problem. So it's a HP problems. So it means from this set you have to see that's a number of possible sets, and from this side you have to find the best one. So best one means this is the maximize the distance. Okay. So
Do you have any assumption on the size of the subset? The size of the subset?
but this is just a typical one. So can I calculate diversity set. That's a length set. Okay. When you so anyhow, this is the two difficult problems. Okay. This is the most difficult ones. Of course, this is still a central research in the data set analysis. So there are many algorithms available to deal with such problems. Typically, I think we have stochastic algorithms. So maybe many of you know that simulated annealing algorithms, that's very popular in the sampling. Look for global minimization. Okay. Also, like genetic algorithms. Okay. So both are very popular in such areas. Also, we have linear program algorithms to work out these problems, and the greedy algorithms. But all of them are very expensive. Too expensive for large data sets. So we needed to look for new algorithms. That's the challenge we face. And the difficulty is when the data sets grow and become larger, how are you going to develop some strategies to deal with the issue? You are not just redo everything. So that's what made quite related to machine learning ideas. So you add a new one, you're going to restructure your data sets, like the diversity sets, for example. That's a very interesting issues. Right. So in this project, we just follow this approach. So actually, I was going to mainly talk about the first step. So in this step, we introduce numerical algorithms, okay, and just reduce high dimension data sets into low dimension data sets. Then we are going to do sampling based on these low dimension data sets to quickly get the diversity sampling, similarity sampling. For example, here, this is I did a test with 832 compounds. Then this compound has been mapping at the 2D. Now you get the figure. So in the figure, so the distance between 2 points indicated the similarity. Okay. So for example, these 2 pairs are very close. We saw they are similar. So now with this mapping, I think chemists maybe can now identify some compounds. And then we're going to do tests. So that's a similarity sampling. You can sample many of them. So then you also can do like a diversity sampling. Now you say this is cluster, and then you're going to pick up like a central one, for example. You see that's the representing. Okay. So that's the idea. With such a mapping, we can simplify, speed up such a similarity sampling or diversity sampling. That would be valuable. Reduce the search time.
Well, those two mapping, they are the same mapping, but you can read for similarity or diversity, right?
That's right.
Of course, the two mapping are the same, same thing, right?
Yeah, this means, for example, this pair, so they're so close. Then I identify actually the two are close. So that kind of you can say strategy, the two are similar. So it means my mapping is pretty reasonable. So it means the value return on the original database in the similarity relationship. So that's the whole story. You have to produce this low dimension mapping that's with that high accuracy in returning the relationship of similarity, diversity from the original database. But how you do that? That's the very challenging issue. Okay. So how you going to produce that low dimension mapping? So this is our approach. Idea is simple. We just combine all these traditional approaches to formulate a new protocol to work out. So all of them have been used in such a problem. Okay. So for example, PCA, similar decomposition, okay, and fast Fourier transform. Truncated is actually fast Fourier transform for signal data compression. So you also can apply to such issues. Right? Of course, they call the distance geometry approaches. Okay, so that's optimization approaches. Okay, so what we do is we're going to use one of them to produce a initial guess for an optimization approach, basically. But what kind of numerical algorithm for solving optimization problems? That's a typical study issue, depends on what you do. Okay. So this is what we do here. Okay. Before we do that, I give a little bit about what's it mean, like distance geometry approach. Okay. Distance geometry problem is a global optimization problems. Okay. So you have to pick up an objective error function, and then you find a minimization solver, and then you have to give an initial guess. So that's three problems you have to consider for any given new database. For example, you want to study, and if you want to carry out this approach, you have to consider these three issues. How you will do them? Okay. So now this is what we do for this chemical database. That's the objective error function. So the objective error function, so we did actually just collect all the error. So you see, this is a mapping in the low dimension. For example, 2D, 3D. This is the original one. And then you do the calculation all the distance. So this is exact value from the original database, high dimension database. And then this is Y is the mapping to the low dimension from the high dimension. Now we want to, this mapping maintain the distance similarity relationships in this sense. So you have this distance. So this distance subject to original distance, you get an error. Okay. Now, what's the new in our approach? Usually distance will be square root if this is Euclidean, right? We got a square. So means for us is a polynomial. Okay, that's to make our approach different from the one people did before. People did before just still contain the square root, and then if you apply derivatives, you may get a singularity points. So means when you apply optimization problem, like use Newton minimization algorithm, that require you calculation of first, second derivatives. If the target function contains singularity, you cannot do them. That's why people always go to similar linear algorithms that do not require any calculation of derivatives. Because the target function is tough. They cannot do it. That's why they do genetic algorithm without doing any derivatives. Of course, if you don't do derivatives, your algorithm will have a very slow rate of convergence. So that's why we try to make an object function that have a good properties. What I mean, they should have like a higher derivatives if possible. Okay, that's the consideration in our future discussion. If you have data sets to study, we have to keep that idea in your mind to do it. Okay. So of course we cannot study why we do that. We argue them. Okay. So that's our errors. And then this is a global minimization problems. So we want for the best one. For the best one. Okay. And then how you going to solve them? So we use, we call the Truncated-Newton Minimization algorithm. So that's a package we developed. We call the team pack. So, and then when we generate the initial gas, use SVD, and then we got the SVD team pack. If we generate the initial gas, use PCA, we got that one, or FFT team pack. So now you are going to produce 3 algorithms for solving these problems. Any questions so far? That's a rough idea. Of course, a lot of details.
So for the definition of omega ij, you have a 1 over delta to the power of 4, right?
Yeah, that's
Is there any
relative.
Yeah, is there any specific reason for the power of 4 instead of 3 or square?
Yeah, the power 4 just need to become a polynomial. And so you can easily calculate the derivatives. And you can use a faster solver for solving these problems. Just simplify your problem. Because you construct the problem yourself. You don't make a difficulty to yourself. that's the idea what I saw. So I make this simple, and then I can solve this one easily. Then faster.
So is the distance only restricted to the Euclidean distance, or can be
Any
another-
distance.
Any distance you
Yeah.
can calculate?
I would say why we use the Euclidean distance, because in the beginning we just work out use SVD, single value decomposition. So single value decomposition mapping from the high dimension to low dimension, they use the first few eigenvalues for single value. Okay, the single values. If we wish to square, that's the eigenvalues. And then mathematically it has been proved. Such a mapping is optimal. It's optimal among all the matrices in the Euclidean distance. So that's a proof. Okay, because that proof, and then that's why when people use SVD to do such mapping, people really think about further improve that one, because they think this is optimal projection already. But for the distance geometry problems, it's not the issue, just as mapping. Most importantly, we want to return the distance similarity relationships. So that's why we have to further refine it to minimize the total error with the distance in the low dimension and the distance in the high dimension. Make them match as close as possible. So that's the reason we have to combine both together, yes.
So if I look at this, the delta ij depends on the distance between xi and the xj. So I suppose the x are the high dimensional vectors. So for your algorithm, isn't it you still need to know the delta ij first?
Their idea has to be given,
Oh,
because that's the whole story.
okay.
Yeah, because delta ij indicated the similarity of between two
That's a given data,
compounds.
right?
That's a given data.
Okay.
That given data. Yeah.
And
So
so
we
when
have
you-
so that you have to try to maintain this similarity in the lower dimension.
So when you
So-
do
so
the
that means,
omega ij is the
Yeah,
tool
you have to
that
keep
will-
that. This is a given. You have to be given that one. So that's why we put distance geometry. So you have a distance matrix. That's a distance matrix. For all the compounds, you have to calculate all the distance. Okay, you have to keep all of them. So actually, this distance geometry has been applied to many other problems, like determine the structure of molecular, like protein, like a crystallographic structure. Usually, you don't know like the pounds. You only know the distance.
So that distance is, that distance is calculatable even x is very large, right?
Yeah, definitely.
Uh-huh.
definitely you can calculate. That's fine. That's because the database there, definitely you can calculate. Yeah, because that's just n square. The calculation. It is.
And that can be
Because you are not repeated calculate. You
Right.
see here,
That
you
can
just
be
calculate
complicated,
once.
yeah.
You calculate once. It doesn't matter. Like take 1 day, 2 day. It's fine. The things why we need a faster solver because sometimes you have to look for repeatedly. Then that's you have to consider faster solver. Otherwise, people don't care. Okay. So that's why in engineering, sometimes the always uses some simple algorithm because they understand. You never use some faster solver because you know what's going on. Are they reliable? Because they don't understand, then they don't trust them. So they all use some slow standard algorithms. For example, when you solve different equation forms, engineers all use a value difference algorithm because they understand them. They really use the value elements to do. The values is more difficult to understand. So that's some issues. Okay.
I could explain why we have the 1/4 there right now or afterwards if you'd like.
Oh, maybe afterwards.
Okay.
Yeah.
Okay. So in summary, this is some advantage of I show here. Simple and well-defined first second derivative, so that we can use Newton-like algorithms. So that's an advantage. So I think another one we can control the accuracy. So we introduce some measurements to work out. So in other words, when you carry out like the mapping, if your 2D mapping is accuracy too low, you have to go 3D. If 3D too low, you go to 4D. You gradually until get the accuracy what you require. So that's it. We have so this is a little idea about the team pack. So team pack has been developed a long time ago. So I did my version for protein potential energy integration. So I improve this using those algorithms. This is the paper you can find. So this is the new advantage in our team pack. Usually we have to keep hashing matrix to be positive definite. Okay, but in our approach, actually we deal with this indefinite hashing forms. This is a mathematical issue. Okay, in practice. So that's why Newton algorithm cannot apply because hashing has to be part of definite. Okay. But how to deal with such an issue? This is an important one. So that's our package is very robust. Like work for positive definite or indefinite forms. So we give the mathematical analysis to say this is reasonable. Okay. Guarantee the convergence. So this is a mathematical issue. And then this is mathematical thing. So I just jump off. Okay, let me just give you some. So this is the package I developed. I think I did this the first 2 years. I was interviewed with one of my students. Actually, we produce a user interface. So based on such packages, interface package here, like a logging package and a database package, and then you have a input, output, And then when you have mapping, you click here, you can show the structure, like you sampling. That's the package I have. So this is the performance. So you see here, if you just use PCA, this is accuracy. If you like in 2 dimension. Now if you apply like refinement using minimization, the accuracy sharply increased 33%. So what it means the accuracy? The accuracy here means the number of pairs less than the accuracy you given. For example, like compounds Xi, substrate compounds Sj, right? The distance less than 10 to the negative 2. And then that's the number of pairs. So like a 33% of distance, 35 accuracy. So if you go to 12, you see, most should be very reliable. So this is from the 300 dimension. Go to 12, you got 92%. That's a high. I think this is a practical version database. You can trust and use that one to sampling. Right? Both of them are very good because you can view them. Right? You can view the points. So you see, this is CPU time. Actually, raise this accuracy to there pretty fast. This CPU time was done almost 15 years ago. I think use a now computer with much faster. That's an older computer. So this is a 2D mapping. You see here. This is PCA. You got the mapping like that. When you apply team pack, now stretch out, you get more details because the accuracy has been improved. So this is compared with the typical one. I think in such a study, like a company or some research group who usually use steep descent minimization algorithms. That's the one they like to use because they're simple, easy to understand. Now you see here, our package compared with steep descent, they run much faster. Much faster. So here, usually for such a minimization problem, you can random pick up start points. That's one approach, random pick up. Of course, this will be much better. Use SVD, generated initial gas. So SVD provides a good initial gas for minimization problems. That's a good one. Why? Because I just attached this file. Okay. So this is like a 3-dimensional mapping figures. Of course, it's more visual. People like that one. Okay, I think that's all. I think in this figure, I just compare with simulated linear method. Then our method is much faster. It's 30 times faster. Simulated linear produce almost the same results. Thank you for the question.
So, if you in your objective function, right? One of the reasons that it's faster is because you have a polynomial that's very smooth, so that you can take second order derivatives for Newton method, right? What if you, let's say, in a neural network training problem where you have a function that's what they call rectified linear, which is not differentiable at 0. So like a function like this, it's a constant and then linear. I mean, it's 0 and then linear. So in that case, can you still use like a Newton technique? Is there any approximation method that can be used to?
Because the does not have a derivative, then you cannot use any derivative related to the Then you have to go to genetic algorithm.
But people use gradient descent in any case, even if the derivative doesn't really exist at 0.
I will not use that. Do not have a derivative.
But can you just, let's say, use a standard modifier to smooth your function at 0? You said that you only have a function which is not smooth at 0.
Right.
So use some sort of approximation for that.
To simulate.
Yeah,
Simulate
people
linear.
didn't. They just directly use the derivative in any case.
Okay.
Yeah. So.
You cannot do that. So that's the difficulties.
Yeah.
Usually, if you use like a normal one, that's really important.
Right. Yes.
So even the function continues, but does not have anything. People try to do that. They call the quasi. They call the
Pseudo.
Yeah. Pseudo Newton. Try to do that. So you can the definition of derivatives. I will not do such a case, but it is a good topic. So because that's in that case you have to extend the definition of derivative to the weak derivative, and then means you have to reform the problem into the weak form. So actually that's the finite element approach. For the difference, always rely on standard derivative, but when the source is tough, then the solution may not have a derivative. Then the differential equation does not make any sense. But people still do that, use the finite difference.
Yeah.
Accuracy very low. So you have to go to redefine the whole problem into variation form, and then solve it using items.
I have a question. So you are using a Fourier transform to do dimension reduction, right? How is that done?
They ask me. Fourier transform.
I think maybe
That's easy.
I'm not sure what he meant, but maybe it's just like DCT when you use discrete cosine transform.
Yes,
So
it's
is
like a wavelength.
Or wavelength.
Yeah.
So because it's a standard thing in comparison, you just select the rows.
It's just a drop. That's
Yeah.
that's small values. Just a drop.
Is that corresponding to selecting rows
Yeah.
of Fourier transform matrix?
So maybe that's more like DCT.
It's not just reduce the row.
The
The mix.
It's depending on how you present the Fourier transform. You can turn 2D into 1D. Then that corresponding to selecting rows. And also the topological indices, are they for manifold? You mentioned at the beginning, sometimes you are using topological indices, right?
You talk about the disruptors.
Right, yeah. This is where yes. So, so that means that for manifold, defined on manifold, right?
We can do that, yeah. You can propose some new disruptors. That's important. If you short some quantity, that's like an invariance, right? And then just use that one. So you will not use someone just related to that. You have to be independent of each other. That's important. Yeah. So actually, I think selection of disruptors are important. You have to carry out some correlation study.
So for the three integration method, the FFT, SVD, and PCA, right? Which one works the best for your data set?
Very close.
Very close.
Of course, the PCA will be some more powerful. So that's I think if you apply PCA, and then that's with some topic for students who work on statistics, because in that way the matrix can be regarded as with random noise. Right. Then you have to calculate the effective values or some other maximum maximize the expected value. Not target function will be changed. Right. So here we just error function. Now we want to maximize the effective values. That's a very good topic for people who work on statistics.
I have to leave. One of my calculus students has to take a makeup test at 1 o'clock, so I have to proctor a test. Otherwise, I would stay longer for questions.
Okay.
But that answers your question about earlier.
So another question I have is, for the searching problem, the similarity, right? You define the error function by assuming the distance will be preserved in two different dimensions, right? High dimensional and low dimensional. But for the searching problem, we don't have to precisely preserve the distance. As long as the distance, the order of the distance is preserved, right? So we don't have to have the precise distance preservation. So that means in the error function, you could probably use a different formula, right? Instead of having the equal distance between the two dimensions, maybe you have some function which can preserve the order of the metric, not the equivalent of the metric. Right?
Yeah, that's good.
Thank you.
I think it relates to that question. So you showed us errors in similarity in this computation of similarity, but do you have errors on actually applying this to some actual task? Like you use the original ones for some task, maybe drug discovery or something like that, and then use this new reduced dimension for that task and see what is the error or the difference you get.
For the drug discovery.
Yeah, some actual application task, like you use the original and then use this reduced one and see what's the difference and what's the error. Because if that preserves that order,
Yeah.
even if there's a 30% error,
Right. We don't care
that
too much,
that
right?
won't make a difference.
Yeah.
Right.
But in the table, you only show the accuracy by comparing the distance, right, in two different dimensions. Yeah.
Maybe in that accuracy table shows the result of the pack, the team pack has a higher accuracy than the PCA. But does that result also maintain the variability that the PCA maintains. The PCA is for the variability. So after the T-impact, so they have the distance relation retained. So will that change the variability?
Because that's the initial gas. It just provide the 20 gas. It may affect the performance of the minimization algorithm. If one maybe a little better, maybe reduce the CD time a little bit, but the results are the same.
Okay.
So I think in the last comparison with similar leaning, just to say, actually, like a team pack, what I use is a local minimization algorithm. But because SVD provides very good initial gas, so the local minimum actually close to the global minimum. That's all. Actually, I'm back to illustrate. Yeah. So that's a high quality. Because like I said, this is a global minimization. You only found the local minimum. So, actually, I did a comparison with several global minimization algorithms to check the accuracy. And that you can find from the papers. Maybe,
Yeah, any other questions? Very nice. Thank you so much. Yeah, that's for today. And this is a fundamental problem of similarity searching or the dimension reduction. This I can see lots of applications in my research. So we try to catch up with the projects here. Hopefully we can use your software, the source code.